Hello, today we'll be talking about quadrilaterals. Now, in case you don't know, a quadrilateral is basically just any polygon with four sides. Like, the most common one is probably a square or a rectangle, but really any shape that has four sides can be considered a quadrilateral. Now there's really two types. Convex quadrilaterals, where all angles are less than 180 degrees, or concave quadrilaterals, where there's one angle that's greater than 180 degrees. You can think of it as um, if it's going inwards, then it's concave. If it's just all going outwards, then it's convex. Now, the diagonal is a segment from one vertex to another vertex that isn't the side. So all quadrilaterals have two diagonals, um, one from this side to this side, one from this side to this side. Here it's a bit more complicated since the diagonal goes outside of the quadrilateral, but it still does count. And a quadrilateral is orthodiagonal if all its diagonals are perpendicular. So for like a square, for example, this diagonal is perpendicular to this one, so that means it's orthodiagonal. And the sum of all interior angles of a quadrilateral is 360 degrees. And just as sort of a proof for that, last time we mentioned how the insides of a triangle were all 180 degrees as well. A quadrilateral is basically two triangles, one angle here, 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 all together. That's two 180s, so that's 360 degrees. Incidentally, you can also prove like the sum of the interior angles of pretty much any polygon, just like, for example, a hexagon, just by splitting this up into triangles. Now let's go into some specific subcategories of quadrilaterals. First, let's talk about a trapezoid. So this is a trapezoid. So it's basically any quadrilateral with two sides that are parallel. So I'll just label this A, B, C, D. So in this case, AB is parallel to CD. And then the parallel sides, these are known as the bases. And then the two on the side, these are known as the legs. And then the distance between the bases of the trapezoid, so from here to here, this is known as the height or the altitude. And the segment which connects the midpoints of the legs. So let's say this is halfway on this leg, this is halfway on this leg. The segment that connects it, that's known as the median. And then the length of the median is the average between the two bases, so that would be AB plus CD divided by 2. And if you think about it, it kind of makes sense because the distance from here to here, that's parallel, it gets progressively smaller, but it decreases linearly up to the top. So then if it's halfway, that means it's really just a half between CD and AB. If that makes any sense, I guess. And next, for the area of a trapezoid, let's say this is B1, B2, and this is the height. Well, the area of a trapezoid is equal to 1/2 B1 plus B2 times the height. And I guess you can sort of prove this and pretend that this is a square, cut it out there, or I guess rectangle, so that would be B1 times height plus, take the two remaining sides, turn it into a triangle, so that would be B2 minus B1 times height divided by 2 because the area of a triangle. So that would just turn into b1 plus b2 minus b1 over 2 all multiplied by height, or you can just simplify it as b1 plus b2 over 2 times height. Now the final bit about trapezoids, just draw another one here. If the two legs are equal in length, so if this side is equal to this side, then this is known as isosceles. And if the two diagonals are equal in length, that also means it's isosceles. And that's just really a rule for trapezoids. Next, let's talk about parallelograms. So if both sides of opposite sides of quadrilaterals are parallel, then it's a parallelogram. So like trapezoids, that's only if these two sides were parallel, but then a parallelogram means this side is parallel to this side, and this side is also parallel to this side. So I'll label this A, B, C, D. So AB is parallel to CD, and also AC is parallel to BD. And the opposite angles and opposite sides of a parallelogram are always equal. So then angle A is equal to angle D, not angle B, angle D, and angle C is equal to angle B. And also the sides are equal, so not only is AB parallel to CD, but it's also equal to CD. And AC is also equal to BD. And the distance between two opposite sides, it's the height, I guess. So this distance here, height. But keep in mind that if you turn it around, then you can also say that this is the height. So there's not really a specific sort of guideline for that, but then the only thing it really matters for is for the area formula, which is equal to base times height, which, if you recall, is basically the same formula as a rectangle. And then, just to kind of show proof for that, imagine you take this, chop it off, and move it here. Well, basically you have a rectangle, and then look, the height is still the same, and then the base is still the same. So then it really just is base times height. Also, some other formulas for it. It's also equal to AB times BC sine B. Not BC, actually it's BD. So basically this side times this side multiplied by the sine of this angle here. Also another formula for it is area is also equal to AD times BC, and if you imagine a cross between it, the angle here, times sine, let's call this E, sine of E. Now there's not really proof for that, but just keep it in mind, I suppose. Next we have a rhombus. For a rhombus, that means 4 sides of the quadrilateral have equal length. So, like this, except drawn a bit better, I guess. these are examples of really badly drawn rhombuses, but then basically all four sides are supposed to have the same length. And an interesting property of this is that when that happens, it's also a parallelogram. But the reverse isn't always true. Like a parallelogram isn't always a rhombus, but a rhombus is always a parallelogram. And all properties of parallelograms apply for rhombuses, or rhombi. So pretty much everything we covered in the parallelogram section. And then the area of a rhombus, well, you could say that it's just use the formulas for parallelograms, or you can say that take the, if I have not a parallelogram, a rhombus, A, B, C, D. If you do AC times BD over 2, that's also the area. So the two diagonals, basically. Also, just as a side note, all the diagonals always are perpendicular to each other, so it's always 90 degrees, and that's why the formula works, because if you split this up, pretend you move this slice over here, and imagine you move this slice over here. Well, basically that's a rectangle, so just this product of the two diagonals. Now finally we have our favorites, rectangles and squares. A rectangle is a quadrilateral that has four 90-degree angles. Note that a rectangle is also a parallelogram, so any properties with that also apply. So this is parallel to this is parallel to this. And the length of both diagonals are equal, so this length is equal to this length is equal to this length, and honestly you don't really need me to tell you that. And the area is equal to length times width, because, you know, why not? And a square is a rectangle with four equal sides, so not only are these sides equal, angles equal, but also the sides are equal. And note that it is also a parallelogram, it is also a rhombus, and the area is equal to the side squared. Also, as a note, the length of the diagonal is equal to side times square root of 2. If you see it, just draw a triangle. This is 90 degrees. This is side. Pythagoras, then you get side square root of 2, basically. Anyways, that's your lesson on quadrilaterals. You may have noticed they're a bit more simpler than triangles. And honestly, triangles are probably the most annoying thing we're going to go over in geometry, anyways. Well, either that or circles. So I guess at this point I'll just give you one fun practice question. So imagine a parallelogram A, B, C, D. And let's say that area is equal to 10. Let's see, AB is equal to 3, BC equal 5. And let's say there's also points, points E, F, and G, so that AE equals BF equals AG equals 2. And note that E is on segment AB, F is on segment BC, and G is on segment AD. So this is on AB, this is on BC, and this is on AD. Now, let's say the line through G parallel to EF is parallel to EF, and it intersects CD at H. So find area of EFHG. And just to reiterate, I guess, so line through G, line G is parallel to EF, and it intersects CD at point H. And once again, your goal is to find the area of EFHG. Anyways, have fun, I guess, and see you next week.